Hey class! Today we're going to be shifting our focus away from absolute value functions and their graphs, and we're going to turn our focus to quadratic functions. Over the course of the next few lessons, we're going to be looking at quadratic functions, their graphs, and we're going to look at the different ways that we can represent quadratic functions. And that first way we're going to look at is what's called standard form. So, we talked about standard form for a linear function. We said that was ax plus by is equal to c. But standard form for a quadratic equation is this: ax squared plus bx plus c. Now, the graph of a parabola looks a little bit like the function we just finished up studying, the absolute value function. That absolute value function had two basic branches that came together to make a v. But a quadratic function, you may recall, is a U-shaped curve, and it's called a parabola. And it looks something like this. And so we're going to see that it has an awful lot in common with the absolute value function that looked like this. So we could use our graphing calculator to see what some graphs of some of these quadratics look like. And so I took and entered this first function, f of x is equal to x squared plus 2x minus 5, which is in that standard form. It's just that the a is 1, right? But that's still standard form. And I put that in my calculator, and I got a few points from the table. It did say sketch, but I just like to get a little more accurate graph, and this is what it looked like. So I put some specific points on here, and I got the graph to look like this. And again, it looks really similar to that absolute value graph. It has this lowest point, kind of like the V does when it opens up, and that point is still called the vertex. And that really means where the graph changes direction. And the vertex of this particular parabola happens to be at -1, -6. Just like the absolute value graph, the parabola is actually symmetric about a line that would actually cut right straight through that vertex, and that's actually called the axis of symmetry. You can see that just mirror images the branches from one side to the other. So then I went ahead and I graphed f of x equals -x squared plus 3x plus 7, and this is what my graph looked like. Now this parabola happens to face downward, and you might notice that the number in front of the x squared, which is called the a in this case, was a negative. So the a was actually -1 in this one, and over here where the parabola opened up, the a turned out to be 1. And it turns out that anytime your a is positive, the parabola will always open upward. And anytime the a is negative, the parabola will open downward. So it's very similar to that absolute value. When we had a negative out in front of the absolute value, it reflected the absolute value graph downward. And that does the same thing with our parabola. So in our leading coefficient, or that a, which is the coefficient of the x squared, is negative, your parabola will open downward, make a sad face parabola. Now you see there still is this axis of symmetry and this vertex. It's just that this time that vertex is the highest point that this graph takes on, and it's sort of like the crest or the top of the hill, and you come back down. But there's still that vertex and the axis of symmetry that basically like a reflecting line runs right through that vertex. So let's talk a little bit more about that axis of symmetry. So the vertical line that divides the parabola, into two equal parts is called the axis of symmetry. Now the axis of symmetry can actually be found by using standard form and the coefficients and the constant term a, b, and c. Because the formula to find the axis of symmetry, well, first of all, it's a vertical line. So it's going to be an equation of the form x equals some real number. But specifically, it's x is equal to the opposite of the b in standard form over 2 times the a in standard form. So if we can identify the a and the b of the standard form, we can use that to calculate the line of symmetry, which would then also tell us the x-coordinate of the vertex, because remember that axis of symmetry runs right through the vertex. And so it's going to have the x-coordinate the same as the equation for that vertical line. Now talking about that vertex more, so the turning point, we said that is the turning point on the graph where that parabola changes direction, and that's called the vertex. And when the vertex is the lowest point, in other words, when the parabola opens up, that's called a minimum value. So we have a minimum if it's the lowest point, and it would be the maximum if it's the highest point. So if the parabola opens down, that vertex actually represents the maximum height that it gets to. And we always want to label these parts on any graph, but specifically on the sketches that we just did, and you can see that we did that. So we labeled the vertex. Actually, then the vertex in this case is a minimum value, so I'm going to put slash minimum. And then here, this is the vertex, and it is a maximum because it's that highest value that it reaches. And if we specifically knew what the coordinates of the vertex were, which in this case, in this first one we did, the second one, it didn't turn out to be on an integer, but we could then write the equation for the axis of symmetry. So just to do this one specifically, x would equal -1 because the x-coordinate of the vertex down here is actually -1. So let's take a look at some quadratics in standard form and see if we can determine if the function has a minimum or maximum, and then if we can find the axis of symmetry and the vertex. So this first one, number 1, f of x is equal to 4x squared. Well, first of all, we know this is a parabola that's going to open upward. It's going to look like this because the a is a positive number. So that means the vertex is going to represent a minimum value, right? Because it opens up, that's the lowest point it ever gets to. So now finding the axis of symmetry. So it's going to be an equation of the form x equals, and to find out exactly what x is equal to, we can take the opposite of b and divide it by 2a. Well, I actually don't have a b listed because, so since it's not there, it really means this is 4x squared plus 0x plus 0. So the b and the c are actually both 0 here. So when I ask you to find the opposite of b over 2a, it's going to be the opposite of 0 over 2 times 4, and anything, or 0 divided by anything is just 0, so that would be 0. X equals 0. Well, remember, x equals 0 is actually the y-axis, so it's actually that y-axis that's going to cut this right straight down the middle, be its symmetry line. If I want to find the rest of the vertex, so I know that the vertex is going to contain that x-coordinate from the axis of symmetry, but to find the y-coordinate, I'm going to take this, I'm going to find out what f of 0 is. I'm going to take that and plug it into the function and see what the output would be that goes along with it. And so when I square 0, of course I get 0. Multiply by 4, I get 0. So this is going to have its vertex at 0, 0. Let's try this next one. So this time, this is a parabola that's going to open downward. I can tell because see how it's got that negative out in front. So if it opens downward, then that vertex represents a maximum. The axis of symmetry is again an equation in the form of x equals some real number because it's a vertical line, and it's going to be equal to the opposite of the b. So this is my b is 6, and my a is -1. So the opposite of b, the opposite of 6 is -6 over 2 times -1. So that's -6 over -2, which makes a +3. So this axis of symmetry is going to be at x equals 3. That means the x-coordinate of the vertex is 3, and to find the y, I'm just going to go ahead and plug it in to the function and see what the outcome is. Now, this is, you got to watch out for that because this is tricky. So the negative is in front of the x squared, but it doesn't go with the x. So what I'm really doing is squaring the 3, then taking the opposite of that, and then adding 6 times 3. So 3 squared is 9. The opposite of that makes -9. And then I add on to that this 18, which is the 6 times 3. So -9 plus 18 is +9. So this is going to have its vertex at 3, 9, and that's really going to represent a maximum value. That's going to be the highest point of that hill, and it comes back down. So let's go ahead and turn the page, and we're going to set these 2, 3, and 4 as you try questions. And in these, you have to do exactly what we just did, which is determine whether this graph opens up or downward so that we can determine whether the vertex represents a maximum or a minimum, calculate the axis of symmetry, and the vertex. So go ahead and pause the video now and give 3 and 4 a try and tune back in when you're done so you can check to see how you did. Pause now. All right, so thank you for trying those and tuning back in. So let's take a moment and check our answers. Number 3 is represents a maximum. The vertex would represent a maximum. The axis of symmetry is the vertical line x equals 0, which again is the y-intercept, or I'm sorry, the y-axis. The vertex is at 0, 7. And number 4, that represents a minimum value because that opens up. The axis of symmetry is at x equals 4. And the vertex is 4, negative 7. So now that we know how to find these key parts of a quadratic function, the maximum or minimum, the line of symmetry, the vertex, let's take all those things and graph some of these functions. And basically we're going to follow these 3 steps as we graph these functions. First thing we're going to do is we're going to find the axis of symmetry and the vertex like we just practiced. Secondly, we're going to find the axis of symmetry and the vertex. We're going to place the vertex as the middle in the row in our table. And we can number up and down on either side of the vertex. And finally, we're going to graph it. And we'll also add a few other little special touches that as we go along, you'll see we can also tell from a standard form of an equation. And one of them is the y-intercept. So let's make a little note here that the y-intercept, it turns out, is the c in standard form. So whatever that constant term is, so the ax squared plus bx plus c, when it's in standard form, that c always represents the y-intercept, which is just exactly what it means when we say the y-intercept for a line. It just means where the parabola is going to cross the y-axis. Now, knowing that piece of information, the y-intercept, along with the vertex and the axis of symmetry, actually allows us to graph quadratics in standard form without necessarily completing a full table of values. Let's go ahead and take a look at some examples and put all this stuff into play. So number 5, the function is f of x is equal to negative 3x squared. So step 1 was to find the axis of symmetry. So to find the axis of symmetry, we're going to use our little formula, x equals the opposite of b over 2a. Well, notice again, we don't have a b, and so it would be the opposite of 0 over 2 times negative 3, which is clearly just going to equal 0. So that's the axis of symmetry, is x equals 0. So if I actually put that on my graph, because this actually represents the y-axis, my parabola is going to be symmetric about the y-axis. So it's going to be a reflection image, one branch over the y-axis to get the other. Now the next thing is I got to find the rest of the vertex. So in order to do that, I'm going to plug 0 into the function, and where x is, and I find out that that is also 0. So this one has its vertex at 0, 0. So right there at the origin is the vertex right there. And I'm going to label that. Oops. I'm going to put it in my table and locate it somewhere near the middle. So say we put it right in here, 0, 0, and that's the vertex. Now I talked about knowing the c or the y-intercept. Well, in this case, because there is no c in standard form, there's no b or c, then we're actually going to have to complete a table to finish graphing this. So you number up and number down, so maybe plug in -1 and -2, maybe -3, and then going forward 1, 2, and 3. And we can just simply substitute those in, and I know that if I square a negative number, remember it becomes positive. So if I square -1, that turns out to be 1 times the -3 is -3. With the negative 2, when I squared, I get positive 4 times negative 3 is negative 12. Take the negative 3 and square it, makes positive 9 times negative 3 is negative 27. And then going into the positive values, I plug in positive 1. Squared is 1 times negative 3 is negative 3. Plug the 2 in, I get negative 12. And plug the positive 3 in, I get negative 27. Now that's not a coincidence. And hopefully you recognize the symmetry. You can see that these values on either side are starting to repeat after the vertex. So going this way, negative 3, negative 12, negative 27, and then going forward, got the exact same numbers here. They're really just, the coordinates themselves are actually mirror images of each other, and they'll of course be mirror images of each other on the graph as well. So let's go ahead and put some of those points on, whatever ones we can fit. So negative 1 and negative 3, so 1, 2, 3 looks right about here. And that's about the last one I'll be able to fit on the left. And then positive 1, negative 3. And we just got these 2 points. And we know what a parabola looks like. It is a curve. So we'll just try to curve it out, but this is actually kind of a skinny parabola facing downward. And so finish it off with some arrows to show it's going to continue on forever. So the last thing left to do is to state the domain and range. And so the domain, I'm able to really plug anything in. I can plug negatives and positives, decimals, fractions, because all I'm doing is squaring it and then multiplying it by negative 3. So all real numbers for my domain, and I can't see the line there, so I'm just going to write it down here. That's the all real numbers. And actually, I'll switch to the other side. So we've got all real numbers for the domain, but you can see that the range is determined by that highest point that parabola ever gets to. That highest point it ever gets to is 0, and all the other values will be that or lower. And if we actually look back at the table there, you can see that all the values, the outputs, were always 0 or smaller. They were 0, negative 3, negative 12, whatever. So we can see that the highest number that ever gets to is 0. So the range is the y values. The y's have to be always less than or equal to 0. All right, let's look at number 6. So again, step 1 is to find out the x of symmetry. So that's using the x equals the opposite of b over 2a. So this time I actually have a b. The b is negative 6, so it's the opposite of negative 6 over 2 times, well, there's not an a listed, which means it's really 1. So that's going to be a positive 6 over 2, which is 3. So my x of symmetry I'm going to put on the graph. It's a vertical line through 3. There's 3 right there. And I just extend that out. That's my axis of symmetry. It's going to be the reflecting line for my parabola. X equals 3. And now I'm going to find the rest of the vertex. So I know the middle of my graph's going to have the vertex there. And it's going to have an x coordinate of 3, and the y I'm going to find by substituting that in to that function. And that gives me 9 minus 18 plus 11. So 9 minus 18 is negative 9, plus 11 is 2. So my vertex is at 3, 2. So it's on the x of symmetry, of course, and it's at 3 and up 2. This parabola is going to open upward. And I mentioned before about this whole idea of a y-intercept. And this actually has a y-intercept of 11. So that's actually, when we talk about the y-intercept, that's actually the value of the function when the input is 0. In other words, when x is 0. So like if I were to go back a few from my vertex, so 2, 1, 0, and I plugged in 0, let's say, I'd actually get 11. That turns out to be the y-intercept. So that point right there is on the y-axis, and that gives us a point that, in this case, it's not a real convenient one to graph. I mean, we could extend out the axis and put it on there, and it would be approximately up here, right there. And because we know that this is a line of symmetry there at 3, we actually could take that point and we could reflect it over, so it actually would be the exact same distance. So if you kind of imagine going back towards that line of symmetry and then just going the exact amount of the same distance, which is 3 more units over on the other side, we could put that reflection image point, and we'd actually see that that gives us then 3 points, and that's really a pretty good number of points for parabolas. Now we could fill out our table. We could get some of the other values. I plugged in 1, I got 6. I plugged in 2, I got 3. I went beyond the vertex on the other side, and I put in 4, which I got 3 again. And I put in 5, and I got 6 again. And of course, then the one I plotted already is when we substitute 6 in, we get 11. So that's the mirror image of that y-intercept. So in the meantime, we could put some of these other points in there if we wanted to get a better shape of the graph. We could put in 1, 6. And here are these other points from my table. And I can just simply connect them and get my parabola. And then as usual, the domain, that's going to be all real numbers because we can put anything into a quadratic function. But clearly, in this case, the lowest that this parabola ever reaches is that lowest or that minimum, remember that's a minimum point because it's the lowest point, it opens up, is that y value of the vertex. So that tells us what we need to know about the range, that y-coordinate of the vertex will always be the maximum point or the minimum point, and in this case it's a minimum, so all the y values will be greater than or equal to that lowest value of 2. So let's quickly work through maybe number 7, and then we will try some tries. So again, the x of symmetry is going to be at x equals the opposite of b, so it's the opposite of -8 over 2 times a, which is 2. So that's 8 over 4, which is 2. So my x of symmetry is going to be at +2. And that means 2, I can place right in the middle of my table. Now to find the y-coordinate that goes along with it, I'm just going to substitute it in. And that turns out to be -2. So that's my vertex. Of course, that's on the axis of symmetry, so over 2 and down 2 would put me right there for my vertex. Because this parabola is going to open upward, I know that that represents a minimum value. And so it's the coordinate there is, again, 2, -2. So if I wanted to complete the table, I could put values in on either side of 2. So like I could put in 1, 0, -1, and then 3, 4, and 5. Or I could just use that point I talked about, that y-intercept. I could plot that point, so that's right there at 0, 6. And then I know that since this is a line of symmetry, the exact same distance on the other side, which is right here, would be another point on this graph. So it's this reflection image. And even just having 3 points really gives us a pretty good idea of what a parabola is going to look like. So we could maybe decide to, which is this, the y-intercept was this point right here, but maybe I could put in one more value. If I substitute 1 in, I would get, if I substitute 1 in, I actually would get 0. If I substituted in 3, I would also get 0, because 3 squared is 9. 9 times 2 is 18. 18 minus 8 times 3, which is 24, is -6, plus 6 is 0. So I could plot those points. There's one right here, and then there's the one at 3, 0. And that's plenty of points to graph that parabola. So I could just connect them. You can see that curves upward like that. Got my parabola. The domain is all real numbers, and that range, that lowest value you can see is, remember, it's always the y-coordinate of the vertex. That's the parameter that you use. So y is going to be, in this case, since it's a minimum, always greater than or equal to that -2. So let's go ahead and actually switch to the next page. We'll just leave, for now, we'll leave number 8 to skip, and we'll turn to the next page and let's assign that one as a U-try. So take a moment, find the axis of symmetry, the vertex, other points, whether it means filling in the table or maybe finding the y-intercept, if there is one, and the reflection of that, and then sketching your graph to determine then the range. We know the domain is, of course, going to be all real numbers, so determine the range, and whether that value is a minimum or a maximum. So go ahead and pause the video now and complete number 9 as a you try. So there you go. That's what the graph should look like. There's a sample table, and that vertex represents a maximum value. The vertex was -1 and positive 0.5, and y values would always be less than or equal to 0.5. So we can also graph piecewise functions that have part of the pieces, part of one of the pieces of the function there was a quadratic piece. So in number 10, that's what we have. We have a piecewise function that has two portions or two pieces, and those pieces divide up at -4. That's where it changes over from being a linear function to quadratic. So there's where this changes intervals. So we may want to make a little table, and if we're going to make a table, remember we have to make one more column than functions that we have because we need one of them for our x's. And we're going to want to put -4 in the middle there and do some values below and above. So I'm going to pick some ones that are just one up and one down from each. And we'll kind of see what we can come up with in our table. So if I'm plugging in up through -4 for the first one, but just not actually including -4, so I'm going to use open dot. So I'll plug in those values, plug in -7, which makes -14 plus 5, and that is -9. And then when I plug -6 in, I got -7. When I put -5 in, that's 2 times -5, -10, plus 5 is -5. When I substituted in -4, I got -3. And remember, that's going to be an open dot. So I'm going to go over here and graph this part. So at -7, -9, just barely be off the graph. At -6, that's a -7. At -5, that's -5. And at -4, that's an open dot at -3. So we're going to want to open dot to show it doesn't actually include it, and then arrow going towards the left where that piece of the function actually exists. But now I'm going to stop putting it in that first function, and I'm going to jump over, and I'm going to start up at that boundary point, and I'm going to start plugging it into the second piece, which is that quadratic piece. So if I plugged a -4 in, I get an output of 4. If I plug -3 in, I get 0. Plug a -2 in, I get -2. A -1 in, I get -2. And at 0, I get 0. So plotting those points, see if that'll give us the shape of that parabola. So at -4, I have +4, so that's right there. At -3, I have 0, which is right there. At -2, I have -2, which is right there. At -1, I have 2. And what that really means, you can tell since those points are right next to each other, then the vertex must be down in between somewhere, like maybe right in there. So it's just below it. And at, let's see, at 0 we get 0. And so this is going to be a parabola that as I connect it, doesn't extend forever to the left because there's that boundary line, but then to the right it'll extend up and have the arrow going towards the right. If I wanted to identify the axis of symmetry, I could see where the axis of symmetry actually was, but to calculate that vertex, I'd have to go through the opposite b over 2a thing, and I find out it's a fraction. But in this case, just getting the piecewise function on the same graph there. But now the domain. So the domain is still all real numbers. I mean, I can plug any number in, and I would find one of these function pieces that I could use based on the interval, because if it was less than a -4 that I chose, I would use the 2x plus 5, and if it was greater than or even equal to, I would use the other part. So that's all real numbers. But now for the domain, that's a little bit tricky. So you can see that the quadratic part actually has its lowest point right around in here. So to actually know what that lowest point is, what we really need to have done is to actually calculate the axis of symmetry, and also to find the rest of the vertex that goes with it. So This one would be the opposite of b over 2a. So the opposite of negative, or a positive 3 is negative 3 over 2a. So 2 times 1, that means it's negative 3/2. And you can see that's where that x of symmetry is, at negative 1.5, in other words. And that's right here, right? So when I plug that negative 3/2 or negative 1.5 back in, I get a negative 2.25. And that's going to tell me what this value is, because this vertex is at that value. So since that's the vertex there, and the lowest it ever gets is this negative 2.25, then in terms of the parabola part, the y values have to be greater than or equal to that negative 2.25. But then there's also a part that goes lower than that, but it starts off at this piece right here. Let me just highlight this. This part right here on the graph, and see how it goes downward forever. So we actually know it's starting at just past that point, which we actually know what that ordered pair was. It was at negative 3, so just beyond that. So the y values will be less than negative 3 as well. So we just have a little gap in there where there's no way you can get either one of those, any of those outputs in between those two key values at negative 2.25 and negative 3, but really you can get any other y value out. So to wrap up this lesson on graphing standard form quadratic functions, we're going to look at graphing quadratic inequalities. So as our typical routine has gone, when we graph inequalities, we basically just graph the boundary, in this case curve, any way that we decide to, whether it be making a table or finding the vertex and the y-intercept and its reflection. And then we decide, once we're able to get the graph, whether we'll use a dashed line or a solid line. And that just depends on the inequality that we use. So again, if we're using a or equal to one, we use the solid curve. And then we shade above or below. So for greater than or equal to, we shade above. And we'll shade below if it's less than or equal to. So let's take a look at one of these together, and then we'll leave one of them as a u-try. So step one is we're going to find that x of symmetry. So this is going to be a parabola that opens up. Its x of symmetry is going to be the opposite of b, so it's the opposite of 2 over 2 times a. Well, the a is 1, so that makes negative 2 over positive 2, and that's a negative 1. So my x of symmetry is right here at negative 1. Substitute that back in. So if I find f of negative 1 and I substitute that in, that's negative 1 squared, which is 1, plus 2 times negative 1, which is minus 2 then. So that's 1 minus 2, and that makes negative 3. And so I know my vertex is at negative 1, negative 3. That's my vertex right there. And then however you want to complete the table, or complete the graph, whether it be extending your table out with like negative 2 and negative 3, and then going forward with 0, 1, and 2, or whatever, or if you want to find the y-intercept, which the y-intercept is this number on the end, this c. So this actually is going to cross on the y-axis at negative 2, so I could put a point there at negative 2, reflect its image over to get a point on the other side right there. Maybe I want to get a few more points, so maybe I plug in, 1 or 2 more numbers. But basically that parabola is going to look like this. But as we know, since this one's a just straight less than, or actually it's a greater than, we want it to be a dashed curve. So you can just either go back through and erase or just make it dashed or dotted to begin with. And then finally the shading. So it says the function is greater than the boundary curve, and that means we're going to shade above. And in this case, it turns out to mean that it's inside the parabola. So again, the key things are finding the x of symmetry, the rest of the vertex, which means finding the y-coordinate of the vertex, locating additional points by either just completing a table or maybe finding the y-intercept and its reflection, and sketch the graph with a dashed or dotted curve and shade accordingly. So we'll go ahead and set number 2 as a u-try question. So if you're ready to try it, you can pause the video and tune back in to check your work to finish up the class. So go ahead and pause now. So go ahead and take a look at the graph, check your work, and if you have any questions, be sure to jot them down, and we'll talk about those when we see you in class.